Hello, I'm Neeraj. So in the second part of the tutorial, I will explain the very important part of variational autoencoder, that is known as variational inference. But before going through this tutorial, I will suggest you to first watch the first part. Otherwise, it will be tough to understand a lot of things. Actually, what happens in the variational autoencoder, the main part of this variational autoencoder is to use some probabilistic encoder to get the latent sample latent variable. That is actually a normal distributions or Gaussian distribution. So based on requirement, maybe any kind of distribution. So that kind of computing that kind of distributions means a fixed size, means a formatted or a very controlled size of output through some uncontrolled or multidimensional data is very tough task. So the computation of probability distributions, computation of conditional probability to get the distribution Z from X, that we can achieve through like probability of conditional probability of distributions X. The computation of this conditional probability, that is posterior distributions, to achieve the distribution X distribution Z using the input X is very tough or intractable, because when we expand these distributions, we found that for the case of multidimensional data, for the case of high dimensional data, multimodal data, it is very tough to achieve some controlled representation. So this is intractable. Again, if we just consider the marginal distributions, even you will see that this is also intractable, because this is an integral of multidimensional data. So the integral of multidimensional data to achieve something controlled is also intractable. So both are intractable. And if we are not able to solve this problem, then it is not possible to achieve the sample latent variable, and then it is not possible to have variational autoencoder. So to achieve this variational autoencoder part, we need something called approximate posterior distributions. That we represent like a Q, and we replace this approximate posterior distributions with this. But now problem is we cannot use any approximate posterior distributions to replace in place of this posterior distributions. So we need to minimize the dissimilarity. We need to maximize the similarity between these posterior distributions with these posterior distributions, and this mapping is known as variational inference. So that's why variational inference is very important. Now how we can achieve this? Now to achieve this, we use the concept of evidence lower bound, and we try to maximize the evidence lower bound part of this equation. So evidence lower bound of a data contains two parts. First part is expectations by using the approximate posterior distributions. By using this, we compute the log likelihood of the data by using the sample latent distributions. And after that, we subtract the KL divergence of approximate distributions and the prior distributions Z. We assume that we have some prior sample latent distributions available. So we will calculate the similarity and then KL divergence score between them and then subtract it from this first part. Now, to get the variational inference in actual training, we need to compute the actual cost functions that will play very important role for variational inference. For that, we need to follow some steps. So the first step is we just concentrate on log of marginal likelihood by considering the approximate posterior distributions, expectations of approximate posterior distributions, and computed for log likelihood of marginal distributions. Now the next step is simple. So next step is we will introduce the latent variable Z, and we will multiply and divide by probability of in this equation. So what will happen? So it will be, if we can write this equation, it is just like some trick and computation trick to achieve something. Then this part will be log of Px into probability distribution, conditional probability of Z given X divided by conditional probability of Z given X. Now this will result in here this will generate joint probability. So it will be like joint probability of log P x z minus log Now let us apply another trick. So this is just a trick by trick. So another trick is we will add and subtract, that is related to approximate posterior distribution. So it will be equal to log equal to EQ, and then we will have minus log Q plus, this is plus and minus, so EQ log, so this plus and minus we added here, and then we will just repeat this part minus so now just to concentrate on this part. it is just a KL divergence. So now the equation will change like EQ expectations with respect to posterior, approximate posterior of ZX. This is joint probability minus EQ plus KL divergence of U double line and then E. So this is KL divergence, and important thing is KL divergence is always non-negative. So in this case what will happen? So we can say that log P of X, sorry, this is like this. So log P of X will be equal to, we can expand this also, means greater than or equal to if we want, we can expand it. And then this part will come minus EQJ log of Q. So this is the final thing. So we can consider that this is the final form of loss equations for variational inference part. So when we use the gradient based method to train this system, we generally try to maximize this part. So this is the part we generally use to maximize, lower bound part, that we need to maximize, so that when we take the approximate posterior, it will actually reflect or maybe very near to close to the actual posterior distribution, and your system, variational autoencoder system, will work. Actually, the loss function of variational autoencoder part generally contains two different things. First is reconstruction and second is variational inference part. So this is the variational inference part of the loss equation. First part is very simple, that I already discussed in the starting of this tutorial. So I don't think that we may require to repeat again. Now next thing is, after all those distributions, how we sample those latent variables, because it will generate a lot of things. So for that we generally use Monte Carlo simulations and reparameterizations based strategy and Monte Carlo simulations to get the appropriate sample latent variables. So these parts are very easy. Just we have to approximate some parts from this part, and then we can easily get those sample latent variable. And at a very low level, how we generally generate the sample latent variable, I already discussed in the previous part, so not repeating this part. So I hope that you are able to understand